So hello everyone, this is lecture 10 for the STR, that is Special Theory of Relativity. In the last lecture I told you the space-like region in the Minkowski's space, and that was this part. This is a space-like structure or the area in the 4D space where means time is not definite here, and the crux was this, that time is not definite, and here we can find that two events can't be at the same place, but they can be simultaneous. Okay, so that's why we can find that here time is not definite. It can be in any order. The sequence of events are, it can be any order in the space like reason, but it's not in the time like. Now we will study the time like. For this I already told you the condition, that is s12 square, that is space time interval, should be less than 0, okay, to be in this region. So this is called time like region. The space inside the cone is time like region. Why it is called time like region? Because here the origin denotes the present when we are observing things, and the upper side denotes future, and the back side denotes past. Okay, because this axis is time axis, and in this time is definite. I will prove this how it is. So time-like region is the region in which Minkowski's space where s12 square should be less than 0. In time-like region, we cannot find out a frame in which both the events are simultaneous. So in this region, there can't be no frame possible when these two events will be happening at the same time. At the same time. How? Just you can observe from this. If these are events E1 and E2, then just rotate your frame anywhere. Means it is like this. This can with this. This can with this. So you can find a frame like this. Like this. So here they are happening at the same position because x dash is 0, but time is different. Time is different because in time axis you can see there is difference in time. It will always be there. There is nothing frame, no frame is possible when these two events will be happening at the same time in this region. That's why we say that time is definite in time like region. And in this frame they can be at the same position. Like in this frame we can see that x is 0. So in the time like region, two events can be happen at the same position. However, we can always find out a frame where both the events will occur at the same position. Means the r12 dash can be 0. Now you can remember by this term that where this thing we heard in the previous lectures. So it was in the time dilation. We see that when there is this clock which is moving, which is in the spaceship or anything which is moving at some speed with respect to the rest frame, then we will observe a dilated time, and that time is observed only when the position of the clock inside that frame is not changing, it is constant. Means the frame is attached to the clock, and if it has some component in that frame, that will remain same all the time. Only then we can observe the time dilation. If you are confusing, then you can go back and see the time dilation back in the lectures. You will be clear about it. So only so time dilation occur in this time like region. Time like region. We will prove this how it is. So in the time like region, we see that if some object is moving in the s prime frame, means it is attached with s prime frame, so its coordinates won't be changing. So r dash 12 will be prime will be 0, and the time in that frame, because the clock is attached to that frame, so that will be the real or original proper time, that is delta t naught. Now in the rest frame we see displacement will be v delta t, which is the speed at which that frame is moving, and delta t, so that distance will give us the r12 coordinate, and the observed time in s frame will be delta t. Now from the equation we heard that it is invariant in the Minkowski's space, so we can write r12 dash square minus c square delta t prime square equal to this. Now we know that r12 prime is 0. Here the delta t prime is real time delta t naught, and here we can write v square delta t and c square delta t square. Now on solving this, we find out delta t equal to delta t prime by root 1 minus v square by c square. This is nothing but time dilation formula. Time dilation formula. So we see that this time dilation occur in this time-like region only. Okay. Why it is not happening in this space-like region? Because here we can't find any space where these two events are happening at the same position. So position is not fixed. That's why time dilation doesn't occur here. It occur only in this region, because here we can find this frame. So for two events in time-like interval, order of time of occurrence is definite because they can't occur simultaneously in any frame. So they can't occur simultaneously in any frame. Means time can't be zero between these two events. Means they can't be at the same time in this region. That's why time is definite. Now we know this equation. This should be less than 0, the space-time interval. From here we can find out that R12 C divided is less than delta t. And what is this? This is the speed, or this is the time at which the information can be sent one place to another. At the maximum speed is c, that's possible. So this time will be less than delta t. So we can see that if event even occurred and we immediately send the information at the speed of light, then we see that the time taken by this information to reach here is less than the event's occurrence time difference. Means this event is not occurred yet and the information is reached here. So he will know that this event is happened first and now this event occurred second. That's why, because of this being less than this, the sequence will be definite in the time-like region, not like this. Here we found that R12CY greater than this. That's why time was greater than this event. So this event occurred already. Now information came. So we don't know that this happened first or this happened first. But here we can know. That's why time is definite in the time-like region of the Minkowski space. Third was the light-like. So we already discussed about it. The region in the Minkowski space where S12 square equal to 0 is called light-like interval. So it's all the cone. All the points on the cone are nothing but light-like region. And here the equation will be this region specifies the propagation of light in 3D space. In 3D space. So this nothing but this represents the propagation of light and satisfy all the points on the cone will satisfy this equation. And here R12 is C delta T. This light-like region is represented by light cone. So that's all in the Minkowski space. That's the question will be mainly theoretical, and if there some questions came, then they will be on the equation of these like this, where the equation is invariant. So you could use this to calculate some things. So now actually our topics are completed for STR. Now in this lecture and next lecture, that will be last lecture, we discuss some questions. So let's start. There is this first question. If half-life of an elementary particle moving with speed 0.9 z in lab frame is this, then find the proper half-life time. So a particle is moving with speed this in lab frame. In lab frame, we found out that time is this. We find the proper lifetime. So proper lifetime will be measured by the observer who is sitting on the frame. So let's say it is delta t naught, and in this frame it is delta t. So delta t naught we need to find, and delta t is given this. We know the v. Let's just substitute the values, and delta t naught will be this. I hope you get it. Next is rod R1 has rest length 1 meter and rod R2 has rest length 2 meter. R1 and R2 are moving with respect to laboratory frame with velocity vi cap and minus vi cap respectively. If R2 has length of 1 meter in rest frame of R1, v by c is given by, so what is given actually, so original length of R1 is given, that is 1 meter. R2 is, we can write it by naught, that is given as 2 meter. and now R1 and R2 are moving like this in the laboratory frame. Okay, so it is moving at vi cap, is moving at minus vi cap. We need to find what? V by c. We need to find v by c. V by c. So how we can find the v by c actually? So in the question we can see, so it is given that if R2 if R2 has length of 1 meter in rest frame of R1, means the length observed by R1 of R2 is 1 meter, but actual length of R2 is 2 meter. Okay, so we need to find the speed of R2 at which it is moving with respect to R1. Okay, then we will have this rest frame and this is moving in this frame, and the speed will determine the length of this. Means we know the formula, L equal to L naught root 1 minus v square by c square. So L naught is 2 meter, L is 1 meter. Now v is here, the speed at which it is moving with respect to this. So v r2 r1 we need to find. We can write it using the equation we already see, that v r2 with respect to left frame minus v r1 with respect to left frame 1 minus v r2l v r1l divided by c square. Now we know that v r2l is minus v I cap and v r1l is v I cap. So substitute the values and find the answer. So then you will just using this formula where R2 is 1 and original length is 2, and you just find the V by C from here. There will be two values, root 3 and 1 by root 3. So root 3 will not be possible because V can't be greater than C. We equal to root 3 C. So this will be the answer, 1 upon root 3. Try to solve this. I will just giving you hints because we already solved this type of question, a lot of questions. So you can just try a little bit and you will be able to solve these questions. Now there is this next question. First see these diagrams. It is given in the question. This is 4c by 5 here. Two spaceships A and B of the same rest length L are moving in the same direction. Same rest length L are moving in the same direction with the speed 4c by 5, 3c by 5 respectively. Where c is the speed of light as mentioned by the B, as measured by B, time taken by A to completely overtake B as shown in the figure in units of L by C is. So what is asking in the question is, if they both are moving in this direction, they both have length L, rest length L. Now if B observe how much time A takes to completely overtake this. So what will be the time measured by B to completely overtake this in units of L by C? Okay, that's what we need to calculate. So for that we just need to calculate how much length it is to pass whole A, and then the speed of A with respect to B. That's all we need. So VA with respect to B will be given by the same formula we used. These are in lab frame. So VA lab minus VB lab divided by 1 minus VLA VLB divided by C square. That will give us VAB will came out to be 5C by 13. So A is moving with respect to B at a speed of 5C by 30. So now we have a speed, but we don't know the length. So if normally in the normal cases we consider it that L and L, it will be 2L. So it can't be 2L. First it need to cross whole B. So in this frame, this length is actually L. So it will cross L. So first we write L. Then the length of A will be contracted according to this because it is moving. It is moving at a speed of this. So contracted length will be L is small, the original length L root 1 minus VAB square by C square. This contracted length. So this will be the whole length. This whole length plus contracted length will give us completely overtake distance. So this is total length. This is speed. Now time can be calculated by distance upon speed. So distance is this divided by 5c by 13 will give us delta T equal to 5L by C. Next question. Distance of a star from the earth. Well, read this question. We already did this in the time dilation when we were discussing the muon problem and all. We discussed this question there, so you can check this out. Just came to the next question. A space crew has a life support system that can last only for 1000 hours. What minimum speed would be required for safe travel of the crew between two space stations separated by a fixed distance of this? So it can be solved by two ways. First, it is given that only 1000 hours. The life support can last only 1000 hours, and 1000 hours is in original frame in the spaceship. Okay, and length is measured in rest frame, that is 12 the hour, so we can write it 15 meter. So this length and this is this, so we can just find this length in the spaceship frame. So if this is the original length, then what will be the spaceship measured, that contracted length will be this L naught root 1 minus the speed at which spaceship is moving, that is given as but that speed is needed to be find, so we can write it. Well, this will be the hard way. We can just go through a easy way, that is we know this distance, this distance in the rest frame of earth. Okay, so we can just convert this time in the rest frame. So it is the time in the, this is the original time given, just convert it in seconds. Then we know that delta t dilated time will be delta t naught by 1 minus v square by c square. Okay, so convert this time, then whatever this comes, now we can write as speed is equal to distance upon time. So distance is given 1.08 into 10 to the power 12, will convert it to 15 meter, divided by speed equal distance upon time now. So it will came to be delta t here, delta t naught divided by this 1 minus v square by c square. Okay, so speed will be this. From here you can find the v term. Actually, you just need to give some values and c, and just calculate v from here. And here, from here we can also see that if just consider this term, it is dilated length actually, and it is the time in the specific frame. So here also we can measure it in both ways. What we were doing here, L was L naught and this way, so this is this length and we divide by delta t naught, or we can write it like this is length and we just calculate the dilated time. So you can go both ways, okay. Well, it's like if there is this time dilation in one frame, then there will be length contraction in another frame, so it just goes that way. So we have this last question now. You need to solve it by yourself. Tomorrow in the last lecture I will discuss its solution and some more questions. So what is this question? A person on earth observed two rockets A and B directly approaching each other with the speed 0.8 c, 0.6 c respectively, at a time when the distance between the rockets is observed to be 4.82 into 10 to the 8 meter. The clocks of the rockets and the earth are synchronized to t equal to 0 second. Time of collisions in seconds of the two rockets as measured in rocket A frame is x by 10, and its answer is x equal to 6. Okay, I gave you the answer, so just try to solve it. Tomorrow I will discuss this and some more questions, and we will done with STR. Then we will start the classical mechanics. Okay, thank you.